Welcome back to Electron Devices and Circuit lecture video series. In this video, we are going to discuss about the operation of N-channel JFET and P-channel JFET. At the end of the video, you will be able to understand the construction and operation of N-channel JFET, P-channel JFET, and the comparison between the BJT and JFET. First, we will see about the construction and operation of N-channel JFET. So this is the construction diagram of N-channel JFET. For constructing an N-channel JFET, initially it is, as I already told you, this is a semiconductor device. It is formed of by P-type semiconductor and N-type semiconductor. So initially you have to take a N-type semiconductor bar, in which the P-type semiconductor, which is a heavily doped P-type semiconductor, is diffused on the middle region on the either side of N-type lightly doped semiconductor bar. These two P-type semiconductor material is internally connected by means of wire, and a terminal is brought out, and it is called as gate terminal. And the one terminal is taken from top of N-type semiconductor, that is called drain terminal, and another terminal taken out from bottom of N-type semiconductor, that is called source terminal. So these two P regions are heavily doped, and N region, that is N-type region or N-type semiconductor, is lightly doped. Keep it in mind. And in order to have a less resistance by tapping the and allow the free movement of charge carriers, so this ohmic resistance or ohmic contact is brought out in each and every terminal. And this is the construction of N-channel FET. Why it is called N-channel means, so here through this channel only the electrons is allowed to flow from source to drain. As I already told you, source is the terminals through which the electrons is entering into the JFET, and drain is the terminal from which the electrons leaves the JFET. And as soon as these two P-type semiconductor is diffused, the two PN junction will be created. One PN junction will be between the gate terminal and drain terminal, and another PN junctions will be around this side P region and surrounding this N region. So two PN junctions will be created. So there exists a space between these two PN junction in N-type semiconductor material that act as a channel. The channel is nothing but the path through which the electrons flows from the source to the drain terminal. Right, so that's why, since the channel is formed by N-type semiconductor material, it is called as an N-channel JFET. Okay, this is the construction, and the symbol of N-channel JFET is this one. So this is the gate terminal and drain and source terminal, and this is the channel. And see here, the arrow mark is entering towards the arrow mark is inward arrow on the gate terminal. This indicates the current is entering into the gate terminal. Right, so here in this type of JFET, the current conduction is only due to one type of charge carriers, that is electrons. That's why it is called as an N-channel JFET, because N-channel is formed by N-type semiconductor. N-type is majority charge carriers is electrons. So this is called as a current conduction is due to only by electrons. So that's why it is also called as unipolar device. That means conduction is due to only one type of charge carriers. So in N-channel, current conduction is due to electrons, whereas in P-channel, it is opposite. The current conduction is due to holes. That we will see later. The next one is the operation of N-channel JFET. In N-channel JFET, we are going to discuss the operation in three cases. One is unbiased FET, and another one is gate source voltage is 0 and drain source voltage alone is applied. And third case is when both VGS and VDS is applied. So we have already discussed the case 1. So this is an unbiased FET. So this is an unbiased FET when no external biasing voltage is given. Biasing in the sense the voltage that is required to bring the device to its activation stage is called biasing. So here see, no voltage is applied between drain and source, as well as on drain and source and gate. So with the structure like this, so there will not be any flow of charge carriers from the source to the drain. The device is useless. And we are going for the second case. So that is the VDD is applied between drain and source and VGS equal to 0. See here, there is no VGS, there is no voltage applied between the gate and the source. So gate and source is left open, and the drain voltage, drain and the source voltage we have to taken into consideration. So before that, we will see the structure again. So here, as soon as so this is a P region, I told you. So this is P region, heavily doped P region, and this is heavily doped P region, and this is an N-type semiconductor bar. So as soon as the P and N region is diffused, the junctions will be created. So one junction is between the gate terminal P region and the N-type semiconductor bar surrounding this P region. And another PN junction is between the P region, which is available on the another side, and the N-type semiconductor surrounding the P region. N-type semiconductor is there. So with the surrounding that, another PN junction will be there. So because of the PN junctions created, there will be a formation of depletion region around the PN junction, and this is the depletion region represented by dotted lines around the P region on both sides. This is the depletion region. See this, when see the depletion region, so this depletion region formations will be uniform around the entire P region on the both sides. The area of depletion region is uniform or same around the entire P region. And one more thing you have to notice, so this is an N-type semiconductor bar. So any type of semiconductor material, by its nature, it is having some bulk resistance. So the bulk resistance that is existing on the drain terminal is taken as RA, and on the source terminal is taken as RB. So this resistance is subjected to vary according to the flow of charge carriers from source to drain or from drain to source. That's why it is represented as variable resistance. So based on this variable resistance, there may be some effect on the width of the depletion region also. Correct. So as of now, you have to keep it in mind. So once if P and N-type semiconductor is one joint, PN junction will be created. Surrounding the PN junction, depletion layer will be created, and this depletion layer, while it is forming, it penetrates more deeply into the lightly doped region than to the heavily doped region. Here lightly doped region is N-type semiconductor bar. So by nature, depletion region penetrates more deeply into the lightly doped semiconductor region. Since here there is no external voltage applied with respect to this circuit, the depletion layer formation will be uniform around the P region. We can say this is either uniform or symmetrical around the P region. Right, so this is the initial case. Now we are coming to the second case. So this is normally second case because unbiased is taken as first case. So this is the second case. Now we are applying VGS is 0. See here, VGS is 0. So VGS is left open and VDD alone is applied. So VDD is always made positive with respect to drain terminal in terms of N channel JFET. In N channel JFET, drain is made positive. So this is positive. So positive in the sense this is in reverse bias because the drain terminal is taken from N-type semiconductor material, N-type connected to positive terminal, this is reverse bias. And here this is also semiconductor bar N-type, that terminal is connected to negative. So we can say source is in forward bias and drain is in reverse bias. So now we will see what happens when this VDD is applied. So when this VDD is applied, what happens? Since this is in forward bias, so here majority carriers electrons, here negative terminal electrons. So repulsions will be there. And here majority carriers electrons, they are attracted towards the opposite terminal of the battery positive. So all the electrons are all the electrons available near the source terminal are forced to move towards the drain terminal. And from the drain terminal, all those electrons leaves out the drain terminal and move towards the positive terminal of a battery, and this results in the continuous flows of electrons through the channel. So I told this as a channel. So channel in the sense it provides the path for the electrons to flow from source to the drain terminal. So initially when I increase the value of VD, drain current starts to increase. So this is because initially if VDD is 1 volt, so the attraction will be somewhat somewhat less. When I increase the value of VDD to 2 volt, 3 volt, 5 volt like that, so here the repulsion will be very high, and here drain terminal to battery attraction will be very high, and as a result of which more and more number of electrons are pushed to move towards the channel, and this results in the increased drain current. More number of electrons are moving towards the channel from source to drain, means it results in more drain current. So the drain current is leaving the drain terminal in this direction. So this results in more drain current, whereas this direction of drain current is nothing but conventional current direction. Normally in circuits we will take only the holes direction now. So that's why here the holes direction is taken as opposite to electrons direction. So as a result, so if VDD increases, initially ID increases. How long this will increase? This will happen only for a particular period of time. After that, what happens means, so if VDD increases, normally more and more electrons increases. That means forward bias on source terminal increases and reverse bias on drain terminal increases. If reverse bias increases, which is nothing but the reverse, the depletion layer increases. Depletion layer is simply acting as a resistance layer. So this resistance RA increases, whereas this resistance RB is in forward bias resistance, so this decreases. So if this resistance increases, the voltage drop on the drain terminal increases. So this voltage drop is further, this increases the reverse bias of the drain terminal. Once if this reverse bias voltage increases, it prevents the further movement of charge carriers from source to drain, and as a result the drain current starts to reduce slowly, and after some time it remains constant. After some time it remains constant. After the particular one particular value of VDD, whatever may be the further increase in VDD, the current will not increase. This is because this depletion layer created by initiated across the drain and the source terminal. This reverse bias voltage that is created across this resistance does not permit the further increase in the charge carriers to move from source to drain, and as a result drain current remains constant. This is because once if depletion layer increases, so the width of the depletion layer penetrates more deeply into the reverse bias side than towards the forward bias side, because the source is forward bias. So as a result, see here both the side depletion layer penetration towards the source is less, whereas towards the drain is more. And as a result on the drain side, reverse bias is again increasing. So as a result the effective width of the channel is getting on decreasing. So after this will happen only for a particular value of VDD. That voltage we call it as pinch off voltage VP. After this pinch off voltage, so the drain current continues to be constant, and it will remains to be in the constant for further increase in drain current. Suppose if we increase the continuously, if we are increasing the value of a VDD, means at one time the breakdown will occur. So whenever there is no gate source voltage, so maximum value of current that is allowed to flow through the FET, that current is called as a drain source saturation current. If VGS is equal to 0 and if we are increasing VDD, initially ID increases to some value of VDD, and after that ID continues to remain constant, and that constant value of current is called drain source saturation current. Right, and the next cases, if VGS is negative and VDD is applied, now we are applying the VGS value also. So let us see now what happens. If VGS is, I told you VGS is always negative with respect to VDD. So gate source, see here the P-type terminal semiconductor connected to negative terminal and N-type connected to positive terminal. So as a result this is said to be in reverse bias. So this is also reverse bias. So now if VGS is negative, if we are applying a small value of VGS, for example if we are applying minus 1 volt. So what happens here, this is in reverse bias. So more and more holes are present here. All those holes are attracted towards negative terminal of a battery, and electrons present here are attracted towards positive terminal of a battery. And as a result of which, what happens means that the width of the depletion layer increases. This is because on either side it is happening. This is also P region. This P region is also what is happening here. This P region is also connected to negative terminal. Right, so this P is also in reverse bias. This P is also in reverse bias. So as a result, the depletion layer penetrates more deeply on either side of the P region. So this P region also increases, this P region also increases, and as a result what happens? The effective width of the channel, this is the channel or path available for the electrons to move from source to the drain. So this again decreases. If we still increase the VGS, still it decreases. If we still increases, again it will getting on decreasing, and as a result we can say that drain current decreases. We can say if VGS increases, so drain current decreases. This is because of what reason? This is because of what reason? The depletion layer effective width of the channel get decreases due to increase in the width of depletion layer. So, and as a result, drain current decreases. So, this will continue if we increase the minus 1 volt, minus 2 volt, minus 3 volt. Like that, if we are increasing the value of negative voltage, the depletion layer is getting on increasing. Effective channel width is getting on decreasing. At one particular value of VGS, these two depletion region touches each other, and there will not be any channel available for the electrons to flow from source to the drain. This will not happen because there is no path for the electrons to flow from source to drain. Entire path will be occupied by the depletion region that is having only immobile ions that does not take part in conduction. So as a result of which the drain current becomes 0. So the value of VGS for which the drain current becomes 0 is called as an VGS off, or otherwise called pinch off voltage, because all the voltage that is contributing for drain current is pinch off voltage. So for what value of pinch off voltage the drain current becomes 0, we call that as VGS off or VGS cut off. Right, so this is the operation of JFET. So this is evident with the help of two characteristics. One is drain characteristics, another one is transfer characteristics. So drain characteristics is nothing but the characteristics plotted on drain terminal of FET. It's nothing but the output terminal of FET. So we have to take the output voltage and output current. See, output voltage is VGS, output current is ID, and this curve is plotted for constant value of VGS. And another characteristics is called transfer characteristics. This is plotted between transfer in the sense we have to take one parameter on output and one parameter on the input side. Normally the output parameter we are taking is current. So normally on the output side we are taking drain current, and on the input side controlling input is nothing but VGS. So VGS is taken on input side, and for this curve is plotted for different values of output voltage VDS. Because when you consider in a FET, we are having only three parameters: gate source voltage, drain source voltage, and drain current. So normally drain current has to be controlled by controlling the gate source voltage. Without gate source voltage, if only drain source voltage is applied, we can able to maintain only the constant maximum value of ID. Under this condition, the transistor is said to be an on switch. If we want to use the transistor as an off switch, either we have to reduce the value of a drain source voltage or we have to increase the value of gate source voltage. In both the cases, the drain current reduces, and once if it becomes 0, the transistor can be brought to cut-off stage. So we can use it in off state. As an off switch we can use. So first characteristics we will see about the drain characteristics. The drain characteristics is plotted by taking the voltage VDS on the x-axis and ID on the y-axis. So when we increase the value of VDS, see here, when VDS is equal to 0, the drain current is also equal to 0. This is because this is an unbiased condition. So both becomes voltage is 0, current is 0. So now if we are increasing the voltage from 0 towards the maximum value, so initially what happens here, the current starts to increase. The collector drain current starts to increases. This is because to some particular extent, so the reverse bias is not that much strong enough to reduce the values of ID. So initially it permits the value of ID to increase. So once if it reaches the point A, you see here, so after which the depletion layer width is somewhat considerable amount. So it prevents the further movement of charge carriers from source to drain, and as a result it reduces the drain current like this. And from the point B, this is the pinch off voltage. So the pinch off voltage is the value of VDS at which the drain current starts to remain constant. So from the point A to point B, it is approaching towards constant. And from point B, it is after which the drain current is considered assumed to be remains constant. So that particular value of VDS at which the drain current remains constant is called pinch off voltage. And after which this will continues for some particular value of VDS, and after one particular voltage of VDS, so the current flowing through the FET drastically increases, and this is said to be breakdown region. After this particular voltage, this is a breakdown region, and this region is called as a saturation region or pinch off region or constant current region, because in this region the drain current is assumed to be remains constant. And this region of operation we call it as ohmic region. Why? Because ohmic means as per the Ohm's law, V proportional to I. If voltage increases, the current also increases. So in this region, if increase the voltage, the current also increases. So this region of operation we call it as ohmic region. And this region, this current is called as a drain source saturation current. So the drain source saturation current, when it will flow? When VGS is equal to 0. For one particular value of VDS, so the maximum drain current starts to flow through the JFET. That current is called as a drain source saturation current, and the value of VDS for which this current flows is called pinch off voltage, right? And this is given by this expression. This was found out experimentally. So ID equal to IDSS into 1 minus VGS by VP whole square. This expression is important in solving the problems. And this is the family of curves for increasing the value of VGS in negative direction. So initially if I am increasing, so this is the case 1. So that means VGS equal to 0. Now I am increasing the negative gate voltage. So now initially VGS is equal to 1 volt. If VGS is somewhat low, it reduces the gate current, that is, and it reduces the collector current. Initially drain current was this much, and now the drain current got reduced to this value. This is because of what reason? If VGS increases, as we identified here, if VGS increases, so depletion layer, width of depletion layer will be very high, and it is going on increasing. So as a result, the effective width of the channel decreases, and as a result, drain current decreases. So that is the reason why drain current is decreasing here. And again, if I am still increasing the value of VGS to minus 2 volt, minus 3 volt like that, still drain current decreases. So this is the value of drain current for VGS equal to 3 volt. So like this happens. And again, if this voltage is called as a breakdown voltage for VGS equal to 4 volt, breakdown voltage for VGS equal to minus 3 volt like that. If we further increase the value of VGS beyond this value for VGS equal to minus 4 volt, the FET enters into breakdown region, and this region of operation we call it as breakdown region. And this is the family of curves, and this curve describes the operations of JFET in drain characteristics. Right, so the next one is the transfer characteristics. So transfer characteristics, we have to take voltage on the x-axis, that is input side voltage you have to take, output side current you have to take. So this is VGS and this is ID. If VGS is equal to 0, what is the current? If VGS equal to 0 means gate source voltage is left open. If it is left open, the current flowing through the JFET is the drain current is the maximum drain current. So that current is called drain source saturation current. So that is maximum here, drain source saturation current. And if we increase the value of VGS in negative direction, so VGS is always negative now, VGS is negative, ID is positive. So that's why the curve is plotted in third quadrant. Sorry, the curve is plotted in fourth quadrant. So this is VGS is negative. If we are increasing the value of VGS in negative direction, the drain current is getting on reducing. At one particular value of VGS, the drain current becomes 0, and this voltage is called VGS cutoff voltage. The value of VGS for which the drain current becomes 0 is called VGS cutoff voltage. This is also called pinch off voltage, because whatever may be the value of VGS, we are telling that as a pinch off voltage. So this is also called pinch off, but more frequently we call this as VGS off or VGS cutoff. And again here also you are using the same expression. From this expression I can able to get the value of VGS equal to VP into 1 minus square root of ID by IDSS. This is the transfer characteristics of N channel JFET. So the next one is the P channel. So P channel construction on operation is exactly opposite to that of N channel. So here the channel is formed by P-type semiconductor and two N region which is heavily doped is diffused on the middle of N-type semiconductor, P-type semiconductor on its either side. And these two regions are internally connected and terminal is brought out called gate terminal, and one terminal on the top of P-type semiconductor drain, and this is source. This is as usual. Since the channel is formed by the P-type semiconductor material here, this is called P channel JFET. Here the current conduction is due to the majority charge carriers, that is holes, because this P-type is acting as a channel here, and only through this channel the charge carrier starts to flow from source to the drain. So that depends on the majority charge carriers present in the semiconductor. So here this is P-type, so current conduction is here due to holes. And this is the symbol of N channel, P channel JFET. Noted down here, this is the gate terminal. Arrow mark is projected in outward direction. So this is the symbol for a P channel JFET. And on the construction and operation side, you have to use, what you have to use for P channel means you can draw the same diagram as such here. But only difference is we have to change the polarity of VDD and VGS, that's all. So VGS should be always reverse bias, and the drain terminal polarity should also be changed here. So when you consider like this is the characteristics. So V and this curve we call it as, this is ID, drain current is negative, and this is VDS. So this is VDS, and VDS we are increasing, so VDS is negative. In the previous case N channel, VDS is positive now. So here we are getting VDS is equal to negative. Since VDS is negative, ID is also negative here. So I am taking this quadrant. This is negative. Actually this resembles fourth quadrant, but this is actually plotted in third quadrant. So VD here, don't forget to represent negative here, that is important. So similarly the same phenomena happens here also. So if VDS is equal to 0, ID equal to 0, and if VDS is continuously increasing, so current also increasing, and after some particular value pinch of voltage, the current assumed to be remains constant, and this is VGS, this is case 1, and we are increasing the value of VGS, so in positive. So because here VGS is positive, this is because VGS has to always reverse bias. When the reverse bias will happen? So this is N type. So N type means positive means reverse bias. So negative should be connected to source because this is P type. So P type connected to negative, N type connected to positive. This is VGS. VGS is always positive here. We have to reverse bias, but VGS is positive with respect to gate. And similarly on the drain side, what we have to do? Previous case we have kept positive, and now VDS is negative here, and this terminal is positive. We have to connect it to the source terminal. This is because if we connect like this only, then only the attraction will be there. So P type majority carriers, holes, all holes will be moved towards positive terminal, and here P type, so repulsion will be here, so more holes will be repelled towards the drain terminal. So the holes current starts to move from the drain to the source terminal. Right, so that's why here in P channel JFET, VDD is negative and VGS is positive. VGS reverse biases the gate terminal, and VDD reverse bias the drain terminal and forward bias the source terminal. Right, that's why they are getting nature of characteristics will be very similar. And next one, transfer characteristics is, here VGS is positive, ID is negative. So this has to be plotted in actually second quadrant. Right, first quadrant, second quadrant. So second quadrant la plot panama, here I have represented it's what ID is negative to represent pannirken. So if VGS is equal to 0, ID is maximum, and if VGS is increasing, ID is reducing. At one particular value of VGS, ID remains 0, and that value of voltage we call it as VGS off, and that value of voltage is VGS off. This may be asked in 2 marks. So this is the transfer characteristics of P channel JFET. And next one is the comparison between the JFET and MOSFET. So, but based on the information you have got so far, you can also able to plot the difference between the JFET and BJT. So BJT, you know, it is a bipolar device. It is unipolar device. Bipolar in the sense current conduction is due to both type of charge carriers. If it is PNP, current conduction is due to both electrons and holes. Whereas NPN also it's like that. Whereas in FET, if it is N channel means current conduction is due to only electrons. If it is P channel, current conduction is due to only holes. So this is voltage control device, this is current control device. Input resistance is very high here, whereas here it is low. This is negative temperature coefficient. That means if temperature increases, current increases. Whereas this is positive temperature. If a temperature increases, current also increases. So switching speed is high compared to that of BJT. FET is having high switching speed, less noisy. Fabrication is very simple and it occupies only less space in IC chip. So compared to BJT, FET is widely used device in almost all analog circuits and digital circuits. Sensitivity is low. Sensitivity in the sense how much amount of input voltage is required to produce a measurable change in output. That is called sensitivity. If I input la evlo small voltage kodutha ennala output la change observe panna mudiyudhu. If collector current change aayirukkuங்கிறது எனக்கு தெரிஞ்சாதா என்னால measure பண்ண முடியும். அந்த change provide பண்றதுக்கு எவ்ளோ value of input voltage வேணும்ங்கிறது தான் sensitivity. Thermal stability is more. This is because whatever may be the changes in the temperature, the FET is more stable. Thermal runaway does not exist in the sense, thermal runaway in the sense, if the device is using for a long period of time, there may be a possibility for getting heat dissipation. If heat dissipation increases, temperature of the device increases. If temperature increases, since this is positive temperature coefficient, current also increases, so this may result in breakdown. Thermal runaway will be more high. So whereas here this does not exist. This is because negative temperature. Whatever may be the increase in temperature, current starts to decrease. So it will not overheat the transistor. So this is a safety purpose. So gain bandwidth product is low. This is the only drawback in case of FET, whereas this is high in case of BJT. So input output relationship is not linear. Here it is linear. What it indicates means if input current increases, output current also increases in BJT. Whereas here, if input voltage increases, if VGS increases, we have noticed in characteristic the drain current decreases. So this is input-output relationship is non-linear. Whereas here it is linear. So these are all the comparisons between two types of transistors. This may be asked in 2 marks or big questions like that. So as a nutshell, we can say how to use this FET as a switch. If you want to use it in an amplifier, switch amplifier use பண்றதை விட this FET is mostly used for electronic switching applications. எப்படி switch applicationல யூஸ் பண்ணலாம் அப்படின்னு பார்த்தனா, இனிஷியலா இந்த FET இருக்கு இல்லையா, இந்த FETக்கு வந்து நம்ம VGS அப்ளை பண்ணாம VDD மட்டும் அப்ளை பண்ணேனா current என்ன ஆகும், maximum current drain saturation current flow ஆகும். அப்ப அது வந்து saturationல ஆப்ரேட் ஆகும்போது அது on switch ஆக்ட் ஆகும். இப்போ நான் அந்த டிரான்சிஸ்டர் switch ஆஃப் பண்ணனும் அப்படின்னு நினைச்சேனா, either நான் இந்த VDD ரெடியூஸ் பண்ணனா drain current ரெடியூஸ் ஆயிடும். அப்படி இல்லைனா நான் VGS அப்ளை பண்ணலாம். VGS -1 volt 2 volt ன்னு அப்ளை பண்ணும்போது பார்க்கறோம் இல்லையா, இப்போ என்ன ஆயிருக்கு பார்க்கும்போது நமக்கு drain current குறைஞ்சிட்டே வருது இல்லையா. எந்த வேல்யூ ஆஃப் VGS அப்ளை பண்ணும்போது drain current 0 ஆயிருக்கோ அது அந்த ரீஜன் வந்து கட் ஆஃப் ரீஜன் ஆகும். drain current 0 னா அவுட்புட்ல current 0, so டிரான்சிஸ்டர் ஆஃப் ஆயிடுச்சு. So இந்த மாதிரி நான் டிரான்சிஸ்டரை ஆன் ஸ்விட்ச் ஆவும் ஆஃப் ஸ்விட்ச் ஆவும் யூஸ் பண்ணிக்கலாம். So இந்த ஒரு அப்ளிகேஷன்ஸ் தான் it is widely used in almost all electronic circuits and switching applications. So hope you got understood about the operations of N channel and P channel JFET. Thank you all. See you back in next video.